Welcome, everyone. I'm excited to kick off our presentation today on chemical kinetics. This is the first slide, so I just want to warmly welcome you all and introduce the topic. Today, we'll explore the fascinating world of how and why chemical reactions happen at different rates. We'll cover some fundamental concepts, key factors influencing reaction speeds, and how this knowledge applies in real-world scenarios. So, let's dive in and discover the essentials of chemical kinetics together. Let's take a quick overview of what we'll be covering in this presentation. Starting with chemical kinetics, which is essentially the study of how fast chemical reactions occur and the factors influencing their rate. We will explore the basic definitions and then move into more specific concepts. We'll look at the rate law, which helps us understand the relationship between reaction rate and concentration. Then, we'll examine different reaction orders, 0, first, and second, and see how they affect the reaction rate. Next, we'll discuss the molecularity of reactions, which relates to how many molecules are involved in the elementary step, and compare that with the overall order of the reaction. We'll also cover the instantaneous rate of reaction, which is the rate at a specific moment, and how it can be determined from graphs and integrated equations. Moving on, the Arrhenius equation will be a key focus, as it relates the rate constant to temperature and activation energy. We'll see how temperature influences reaction rates and how catalysts can lower activation energy, making reactions faster. Collision theory is another fundamental concept, explaining how molecules must collide with sufficient energy and proper orientation to react. We will also look at specific types of reactions, such as first-order reactions, their half-life times, and zero-order reactions, along with real-world examples to illustrate these ideas. Finally, there will be an assignment to reinforce what we've learned, and we will wrap up with explanations of the Arrhenius equation and the effect of catalysts. Throughout this overview, our goal is to connect these concepts cohesively, emphasizing their importance in understanding chemical reaction mechanisms and kinetics. Today, we're diving into chemical kinetics, which is a fascinating branch of chemistry focused on understanding how fast reactions happen. Essentially, it looks at the rate or speed of chemical reactions and what influences that speed. We explore factors like temperature, concentration, catalysts, and surface area, all of which can speed up or slow down reactions. Furthermore, chemical kinetics also examines the mechanism of reactions, meaning the step-by-step process that molecules undergo during a reaction. By understanding these mechanisms, we can better predict reaction behavior and even control it for practical applications. This area is really crucial because it connects the fundamental principles of chemistry to real-world processes, like industrial manufacturing, pharmaceuticals, and environmental chemistry. So, as we move through this presentation, keep in mind that chemical kinetics helps us understand the how and why behind reaction rates, which is key to mastering chemistry's practical side. Now, let's talk about reactions that fall somewhere in between slow and fast reactions. These are called moderately slow reactions. They don't happen instantly, but they also don't take years. Instead, they usually take from several minutes up to a few years to complete. Examples of such reactions include the inversion of sugar and the hydrolysis of starch. These reactions are important because they help us understand how some processes occur over a period of time that's manageable, but not immediate. Moving on, we have the slow reactions. These are reactions that take quite a long time, ranging from minutes to years, to finish. Think of rusting iron or the transformation of diamonds. These processes happen very gradually. Recognizing these helps us understand natural and industrial processes that are slow but significant. Finally, the fastest reactions are the ones that occur almost instantaneously. These can happen in just 10 to the power of -16 to -14 seconds. A good example is ionic reactions, which happen extremely quickly. Overall, categorizing reactions based on their rate helps us understand their behavior and the conditions under which they occur. Today, we're going to talk about what we call the average rate of reaction. Essentially, this is the change in the concentration of any reactant or product over a specific period of time. So, When we measure how quickly a reaction occurs, we're looking at how much the concentration of substances involved changes per unit of time. It's important to understand that this gives us a way to quantify the speed of a reaction, providing a clear picture of how fast or slow a process is happening. By examining these changes over a defined interval, we can compare different reactions or see how conditions influence reaction rates. This concept ties into our overall discussion on reaction kinetics, helping us understand the factors that affect how reactions proceed over time. Now, let's talk about the change in concentration of reactants or products at a specific moment in time. This is what we call the instantaneous rate of a reaction. Essentially, it tells us how quickly the concentration is changing exactly at that very instant. Unlike average rate, which looks at the change over a period, the instantaneous rate zooms in on a single point in time. This concept is crucial because reactions are constantly evolving, and understanding the rate at a specific moment helps us grasp the reaction's dynamics more precisely. It connects to the overall theme of reaction kinetics by giving us a detailed snapshot of how fast reactants turn into products at any given moment. Let's take a closer look at the factors that affect the rate of reaction. First, surface area plays a crucial role. When the surface area increases, it provides more opportunity for the reactant particles to come into contact or collide with each other. This naturally results in an increased reaction rate because more collisions mean more chances for reactions to occur. Next, temperature is another key factor. As we increase the temperature, the particles move faster and collide more energetically, which again speeds up the reaction. Moving on to concentration. When the concentration of reactants is higher, there are more particles in a given volume. This leads to more frequent collisions, and thus, a faster reaction rate. Finally, the nature of the reactant itself influences how quickly a reaction proceeds. Ionic reactions tend to be quite fast because of the strong electrostatic forces at play, whereas reactions involving covalent compounds tend to be slower due to the different bonding characteristics. In summary, these factors, surface area, temperature, concentration, and the nature of the reactant, all interact to determine how quickly a chemical reaction occurs. Understanding these helps us control and optimize reactions in various applications. Let's take a closer look at the rate constant of a reaction. It's important to understand that this constant is equal to the rate of reaction when the concentration of each reactant is at unity, meaning 1 molar. This gives us a standard reference point to compare how fast reactions proceed under different conditions. Now, moving on to the rate law, this is a key concept. The rate law is an expression that describes how the reaction rate depends on the molar concentrations of the reactants, and what's really important is that this expression is determined experimentally. So, rather than just guessing, we measure and find out how the concentrations influence the rate in real scenarios. In essence, the rate law helps us quantify the relationship between concentration and reaction speed, which is fundamental to understanding and predicting reaction behavior. It ties together the reaction's kinetics with the molar concentrations, giving us a powerful tool for analysis. Let's talk about the order of a reaction. When we say the reaction is first order with respect to A and second order with respect to B, meaning A equals 1 and B equals 2, then the overall order of the reaction is simply 1 plus 2, which equals 3. We call this an overall third-order reaction. Now, it's important to remember that the reaction order is determined by experiments, not just theory. Reaction order can be positive, negative, 0, or even fractional, depending on how the concentration affects the rate. For example, if a reaction is first order with respect to A and 0 order with respect to B, that is, A equals 1 and B equals 0, then the overall order is 1 plus 0, which equals 1. In this case, we call it an overall first-order reaction. Similarly, if the reaction is first order with respect to both A and B, meaning A equals 1 and B equals 1, then the overall order is 1 plus 1, which equals 2. That makes it an overall second-order reaction. To put this into context, consider the reaction. AA plus goes to P, for example, the reaction H2 plus I2 forming 2H. The reaction order here is the sum of the powers of the concentrations, which are M and N, so the reaction order equals M plus N. And finally, the rate law can be expressed as the rate equals some constant K times the concentration of A raised to the M power times the concentration of B raised to the N power. The key takeaway is that the overall order of the reaction is just the sum of these individual powers, which tells us how the rate depends on the concentrations of the reactants. Let's take a closer look at molecularity, which is a fundamental concept in understanding reaction mechanisms. In general, the molecularity of a simple reaction is equal to the sum of the number of molecules of reactants involved in the balanced stoichiometric equation. Essentially, it tells us how many molecules need to come together for the reaction to occur. Molecularity is defined as the minimum number of molecules, atoms, or ions of reactants required for the reaction to take place. Think of it as the number of particles that must collide simultaneously for the reaction to proceed. It is directly related to the stoichiometric coefficients in the balanced chemical equation. So, the molecularity is equal to the sum of these coefficients for the reactants. Looking at the table, we see different types of molecularity. For example, when a reaction involves only one molecule, like PCl5 breaking down into PCl3 and Cl2, we call it unimolecular. In this case, only one molecule needs to decompose or react for the process to happen. When two molecules are involved, like in the reaction between hydrogen iodide molecules to produce hydrogen and iodine gases, it is bimolecular. Here, two molecules must collide for the reaction to proceed. Similarly, when three molecules participate, such as in the oxidation of sulfur dioxide to sulfur trioxide, we call it trimolecular. It indicates a more complex interaction involving three particles. By understanding molecularity, we gain insight into the reaction's complexity and how particles interact at the molecular level. This concept helps us predict reaction rates and mechanisms, which ties into the overall theme of understanding chemical behavior at the molecular scale. Let's take a closer look at the difference between molecularity and the order of a reaction. Molecularity refers to the number of reactant molecules involved in an elementary step of the reaction. It's a theoretical concept, meaning it's based on the reaction mechanism itself. For example, if a step involves two molecules colliding, it's bimolecular. It's always an integer, so it can't be zero or a fraction. On the other hand, the order of a reaction is determined experimentally. It tells us how the reaction rate depends on the concentrations of the reactants. The order is calculated by adding up the exponents in the rate law, which are derived from experimental data. It's important to note that while molecularity is a theoretical property and always an integer, the order of a reaction can be a whole number, a fraction, or even zero, depending on how the rate depends on the concentrations. Connecting these points, understand that molecularity gives us a picture of the reaction mechanism at a molecular level, while the order describes what we observe in experiments. Both are essential for understanding how reactions proceed, but they come from different perspectives, one theoretical, one experimental. A reaction is said to be of zero order if its rate is independent of the concentration of the reactants. This means that, unlike other reactions where the rate depends on how much reactant is present, in a zero-order reaction, changing the concentration doesn't affect the speed of the reaction. This typically occurs under specific conditions, such as when a catalyst surface is saturated, or when the reaction involves a step that is independent of the reactant concentration. Understanding zero-order reactions helps us see how certain reactions can proceed at a constant rate regardless of the amount of reactant, which is a key concept in reaction kinetics and helps us predict reaction behavior under different conditions. Let's take a closer look at this slide, which shows an integrated equation alongside its corresponding graph. What we're really highlighting here is how the equation and the graph work together to give us a complete picture of the concept we're exploring. The equation provides the precise mathematical relationship, while the graph offers a visual interpretation, making it easier to see how the variables interact over a range. One of the most important points is understanding how changes in the equation affect the shape and position of the graph. For example, tweaking certain coefficients can shift the graph vertically or horizontally, or alter its steepness. Recognizing this connection helps us not only interpret the graph more effectively, but also predict how modifications to the equation will influence the overall behavior. This integrated approach ties into the broader theme of the presentation, showing that math isn't just abstract symbols. It's a powerful tool for visualizing real-world phenomena. When we combine equations with graphs, we enhance our ability to analyze, communicate, and understand complex relationships in a more intuitive way. Let's take a closer look at this rate equation. The rate of the reaction is equal to the negative change in concentration of A over time, expressed as dA/dt, and this equals K times A, which is the concentration of A at any given time. This is our fundamental differential equation for a first-order reaction. Here, A0 represents the initial concentration of A before the reaction starts, and AT is the concentration of A after a certain time t. This helps us track how the concentration changes as the reaction progresses. Now, considering the reaction a converting to products, what makes a reaction first order is that its rate depends solely on the concentration of one reactant. In this case, the rate is directly proportional to A, which simplifies analysis and modeling. Understanding this concept is crucial because first-order reactions are common in many chemical processes, and this rate law gives us a straightforward way to predict how concentrations evolve over time. It ties into the overall theme of kinetics, how reactions proceed, and how we can quantify their speed. Now, let's talk about the half-life of a first-order reaction. The key point here is that the half-life, which we denote as T12, is given by this simple expression. 0.693 divided by the rate constant, K. This means that the half-life is inversely proportional to the rate constant, so as the reaction speeds up, the half-life gets shorter. To put it another way, T12 equals 2.303 times the logarithm of 2. Divided by K, this comes from the natural logarithm basis, and it's a handy way to relate the half-life directly to the rate constant. Now, if we want to find the value of T12 from the rate constant, we can rearrange this equation. So, K equals 2.303 times T12 times the logarithm of the initial concentration over half the initial concentration, which is A0 divided by A0/2. Here's a crucial point. At the half-life point, the concentration A is exactly half of the initial concentration, A0/2. If we substitute this into our expression for the rate constant, we get a new form. K equals 2.303 times T times the logarithm of the initial concentration over the current concentration, A. So, summarizing this, for a first-order reaction, the rate constant K can be expressed mathematically as this. It links the reaction's half-life directly to the rate constant, helping us understand how quickly the reactant concentration decreases over time. This concept is fundamental because it allows us to predict how long a reaction will take to reach a certain point, which is critical in many practical applications. Let's take a closer look at the rate law for this reaction. It can be written as rate equals K times CH3 Cuc2H 5 times H2O. Now, an important point here is that water is present in large excess. Because of this, its concentration stays practically constant throughout the reaction. This allows us to simplify the rate law from rate equals K times both concentrations to rate equals K times just CH3 Cuc2H5, where K is a modified rate constant. This simplification is very useful because it makes the reaction easier to analyze. Even though the overall reaction involves two molecules, an ester and water, it actually follows what's called pseudo-first-order kinetics. That means, in practice, it appears to behave as a first-order reaction, which simplifies kinetic studies. So, to sum up, the hydrolysis of an ester, like in this example, is second-order overall, but because water is in excess, it acts as a pseudo-first-order reaction. This concept is key in understanding how reactions can be simplified under certain conditions, especially in practical laboratory settings. So, what we see here is that the rate constant for a chemical reaction nearly doubles when the temperature increases by just 10 degrees. This highlights how sensitive reaction rates are to temperature changes. Now, before 1889, scientists didn't have a precise way to measure how temperature affects reaction rates physically. It was quite a challenge to quantify this relationship. Then, in 1889, Svante Arrhenius introduced a groundbreaking equation, now famously known as the Arrhenius equation. This equation provided a mathematical way to describe how temperature influences reaction rates, which was a huge step forward in physical chemistry. Understanding this relationship helps us predict reaction behavior under different conditions, tying back to the overall theme of how temperature controls chemical processes. Certainly, here's the word-by-word narrative script for slide 18. Now, this concept was first proposed by the Dutch chemist J.H. van 't Hoff, but it was the Swedish chemist Arrhenius who really provided the physical justification and interpretation for it. When we look at the equation, A stands for the Arrhenius factor, or the frequency factor, which is also called the pre-exponential factor. It's a constant that's specific to each particular reaction, reflecting how often the reacting molecules collide with the proper orientation. R is simply the gas constant, a key value in thermodynamics, and E is the activation energy, which is the minimum energy required for the reaction to proceed. Understanding this equation helps us see how temperature influences reaction rates, and it's a fundamental part of kinetic theory. E, or activation energy, doesn't depend on temperature, volume, pressure, or other external conditions. Instead, it is affected by the presence of a catalyst, which can lower the activation energy needed for the reaction to proceed. For a specific reaction, E remains constant, meaning it doesn't change as conditions vary, but the catalyst can modify it. Now, when we increase the temperature, more molecules have enough kinetic energy to overcome this activation barrier. As a result, a larger fraction of molecules can reach or exceed the activation energy, leading to a higher reaction rate. This explains why temperature increases typically speed up reactions. To understand this better, consider the Arrhenius equation. It relates the rate constants at different temperatures, K1 at T1 and K2 at T2. The key points here are that the activation energy is the extra energy molecules need beyond the threshold energy, ET, to convert reactants into products. Remember, the threshold energy is the minimum energy required for reactants to start transforming into products, while the activation energy is the additional energy needed to reach that threshold. According to the Arrhenius equation, for a reaction to happen, molecules must collide with enough energy to form an unstable intermediate. This intermediate exists only briefly before breaking down into products. The energy needed to form this unstable intermediate is precisely what we call activation energy, E. So, in summary, the temperature affects the fraction of molecules with enough energy to react, thereby influencing the reaction rate. The presence of a catalyst reduces E, making it easier for molecules to react at lower energies, which is a crucial concept in understanding reaction kinetics. A catalyst provides an alternative route for the reaction with a lower activation energy. This means it makes it easier for the reaction to occur, without being consumed in the process. The action of the catalyst can be explained by what's called the intermediate complex theory. According to this theory, a catalyst actually participates in the reaction by forming temporary bonds with the reactants. These bonds create an intermediate complex, which is a sort of transitional structure. This complex doesn't last long, it's transitory. Eventually, it breaks apart, decomposing to produce the final products and regenerating the catalyst. So, essentially, the catalyst helps lower the energy barrier, speeding up the reaction, and then it's free to do the same for other reaction cycles. This process highlights the crucial role catalysts play in many chemical reactions, making them more efficient and faster. Let's take a closer look at this key equation. The rate of reaction is equal to ZAB, which is the collision frequency of reactants A and B, multiplied by e to the power of negative e over RT. Now, ZAB represents the number of collisions happening per second per unit volume between our reacting molecules. But not every collision leads to a reaction. Only those collisions where the molecules have enough energy, specifically, at least the activation energy, and are correctly oriented to react are considered effective collisions. This is crucial because it highlights that simply colliding isn't enough. The energy and orientation matter a lot. The exponential term, EE/RT, captures this idea. It's the fraction of molecules that have enough energy to overcome the activation barrier. In terms of the theory, we assume that molecules behave like hard spheres, and a reaction occurs when these spheres collide with sufficient energy and proper alignment. This helps us understand the factors influencing reaction rates, emphasizing that increasing temperature or collision frequency can speed up reactions by making effective collisions more likely. So overall, this equation and the concept of effective collisions tie back into the broader theme of how molecular interactions govern reaction kinetics. Let's take a step back and look at the overall view. This slide summarizes the key points we've discussed throughout the presentation. First, we emphasize the importance of understanding the core concepts, which serve as the foundation for everything else. Next, we explored how these concepts can be applied practically to solve real-world problems. We also looked at the benefits of adopting this approach, including increased efficiency and better decision-making. Finally, I want to highlight how all these elements connect to the overarching theme of innovation and continuous improvement. When you see the bigger picture, it becomes clear how each piece fits together to drive success. This overall view helps us appreciate the interconnectedness of everything we've covered and underscores the importance of integrating these ideas into our work moving forward. Let's go through some key questions to wrap up our discussion. First, what is the difference between order and molecularity? Order refers to the power to which the concentration of a reactant is raised in the rate law, indicating how the rate depends on concentration. Molecularity, on the other hand, is the number of molecules colliding in an elementary step, so it's usually a whole number like uni, bi, or termolecular. Next, what is the unit of the rate constant for a second-order reaction? The unit is typically expressed as liters per mole per second, or L-mol 1s1. This helps us understand how the rate constant scales with concentration. Moving on, what exactly is the Arrhenius equation? It's a formula that relates the rate constant to temperature, showing how increasing temperature increases the reaction rate. It's written as K equals a times e to the power of negative e over RT, where A is the frequency factor, E is the activation energy, R is the gas constant, and T is temperature in Kelvin. Now, let's define collision theory and the Arrhenius factor. Collision theory suggests that reactions occur when particles collide with sufficient energy and proper orientation. The Arrhenius factor is the exponential term e to the power of negative e over RT, which quantifies the fraction of molecules that have enough energy to react at a given temperature. What about the integrated equation of a first-order reaction? It's expressed as ln A minus ln A0 equals negative KT, or more commonly, A equals A0 times e to the power of negative KT. This shows how the concentration decreases exponentially over time. Finally, how does temperature influence the rate of reaction? Generally, as temperature increases, reaction rate increases as well. This is because higher temperatures provide more energy to molecules, increasing the number of collisions with sufficient energy to overcome the activation barrier. That covers our key points. Remember, understanding these concepts helps us grasp the fundamental principles behind reaction kinetics and how reactions proceed in different conditions.